Hey, good afternoon, everybody. So first, few announcements. This Today is the due date for homework 3 or, or 4. I don't 4. Yeah, because we kind of extended for a couple of weeks the due date, so I'm I'm lost. Yeah, for attention. And second announcement is that we don't have class this Wednesday because of the career fair, and we will have class only on Friday. And the last announcement is that I updated the last class notebook and added a little bit clarifications about how to download the models. So this is homework 6 notebook. So I learned that the first model doesn't support API on Hugging Face. Then I added a little bit more information about quantization. So for example, if you want to upload the weights in lower precision with parameter quantization config, it will quantize during the uploading. So it will take some time. If you want to upload quantized model in advance, then you can just use some models with for example, this GPTQ method for quantization, so it will be faster. So what else? I think that's it about previous homework. And also from one of our previous weeks slide, I just didn't mention that when we talked about benchmarks, on the slides there was this code, and this is the convention that if we cite these benchmarks, we should add this token, which is unlikely to see in other texts. So when the model is trained again on data from internet, it says that those are data from benchmark that it shouldn't be trained on. But of course, you can imagine that not all people will include this token in their web pages or presentations, and we can't guarantee that data that model was actually trained on this data instead of the model kind of performed the task on the new data. Okay, so today, and actually I have one more announcement. We're now at week 7. It means that you can choose any homework from this week 7 and later for your final project. So this week we will talk about fine-tuning large language models. And in homework, there will be a task that you can choose as your project, so you don't need uh, to complete the entire homework. And the same will be for the remaining homework. So like after break, we will talk about reinforcement learning, then quantization, and you can use a part of homework as your final project. Okay, so when we talked about BERT model, we trained the entire model. If we wanted to force our model to perform some tasks, we trained all the weights. You can do the same with GPT-2 model, but with larger models, the weights won't fit the memory. So if you want to train the model, you should allocate at least 3 times more space because it will use gradients, and Adam optimizer will also save parameters, 2 parameters like run average and variance. So for every weight, you will need to allocate 4 times more space for gradient for 2 parameters from optimizer. And if your model weighs 7 GB, for example, you should allocate about 28 or 24 GB. So that's why in practice, if you want to train large language model, it's not a good idea to train it in the 32 or 16-bit precision, or to update all the weights. And the topic of this week is parameter efficient fine-tuning. So how can we actually train large language models efficiently on relevantly small GPUs, like 16 GB or 24. And first of all, why do we want to? Well, next week we will talk about chat models, but fine-tuning actually is used to train large language models as chat models. Uh, it just the first step is to fine-tune the model on the data of conversations. So this is one of the reasons why do we want fine-tuning the models. And maybe I can show example of the chat bot that I created last week. So there is POE API where you can create a chatbot. So let's see. So I created a chatbot with a prompt, and you can write here, for example, instruction, and I created a chatbot that proves everything negative that the user says. So you can provide instruction. Again, we will talk about instructed models next time when we will talk about chat models. But it just interesting example. For example, listen to the user and um, provide to, um, hmm, reason, for example, is um, and let's create this agent, and we can, for example, write I assume that the Earth is um, not flat. The chat will actually prove that the Earth is flat. So, and provide summaries like Egyptians thought differently. So, yeah, and the first step to force the standard language model that just generates new token to um, perform the chatbot is to train this model on the conversational data. And if the model is large, like 70 billion parameters, it's hard to train the entire model. So we should use another way. So let's talk about the other ways to tune the model. So let's one last time. So today it will be just lecture, and on Friday we will do the code and actually fine tuning. So remember we talked about prompt engineering. Oh, by the way, one more comment. I added the to the work page for previous week a guideline about prompt engineering for different models. So if you open that, it provides different ideas for prompt engineering and for different models. Um, like you can look at the examples. Okay, so let's go back to today's topic. So prompt engineering. Last time we talked about how to force model to perform a task with some examples. And we called this few shot prompting. The idea behind that was that, well, actually, um, Robert, I think Robert can tell us more about prompting. Robert, I think you can tell us about prompting a lot because you use prompt engineering for the educational project. So um, I have one question. Uh, you use the ChatGPT API, and the API is changing. So did, did you notice any changes in your educational chatbot? Because you didn't change the prompts, but the model has changed. Did you notice any differences?
Yes, the prompts are not portable between models. If we take one prompt that we know works well for one model and we apply it to another prompt, the results may be very different.
Yes. So this is only another another reason why sometimes we want to fine-tune the model and just train instead of using ready prompts, because if the version of the model is changed, then the prompt that worked well can work differently for new model modification. And the idea behind that was that, like, the starting prompt, the starting tokens, somehow force the model to perform the desired task. So the first idea was, if we try to find some tokens for the prompt, why we don't learn these tokens? Because the tokens are embeddings, so we can create just, for example, 10 vectors and update parameters only of these vectors. So it's called learnable prompt. What they will learn, I think we will see some examples. So they won't have any sense to us, but this learned prompt actually will force the model to generate desired output. And you will do this in your homework as well. So we just create, for example, if the embedding shape is 1024, we will create just, for example, 10 vectors, and we will train the matrix of size 10 times 124. All other weights of the model will be frozen. So it is very really light fine-tuning. So you will just tune the prompt. And this is called prompt tuning. Here's the comparison between the tuning of the entire model. Green line corresponds to prompt tuning, like um, learned prompt, and blue is represents when people try to different prompts, try to choose the best prompt, and you can see that this simple idea to learn the prompt gets higher performance than human created prompt, but lower than full model tuning. And by the way, it's also interesting that um, the accuracy depends on the size of the model. If the model is small, so 7 billion parameters, about here. So then both end prompting and learnable prompt, and fine-tuning, they actually don't work well. But with increase of the size of the model, so I believe there is no continuation of this curve because it's impossible to fine-tune entire large model, but there is a blue line that corresponds to the prompt. So yeah, with this learnable prompt will work well for large models only. So this is another idea. You can learn not only the input embeddings, you can also learn the embeddings for latent layers. Because you remember in transformer, there are several transformer layers. So you can also learn this first couple or two tokens for every hidden layer. The next idea was to add some trainable layers inside the transformer model. So it's called adapters. For example, this feed-forward layer in the transformer has the shape of 8000, for example. And you can add one more layer between these two feed-forward layers of much smaller size. And unfreeze only this additional layer, which is called adapter. But in practice, let's see, here is the comparison. The difference is not very large with adapters. So in practice, currently is used another modification of this adapter, which is called low rank adapter, LoRa. And instead of using additional layers in between our model, low rank adapters will be used as additional weights in every linear layer. Do you remember which are linear layers in transformer models? Where do we have linear layers in transformers? So you did your homework on attention. Are there any linear layers in attention, for example? Well, there are four. So 3 for embeddings and 1 for attention. But for heads and 1 for heads. If we have multi-heads, then there is a layer which is applied to concatenated heads. So for 4 at least. Then in FFN layer, there are 2 linear layers. So we can extend all these layers. So blue layer represents this linear layer. Actually, in this, yeah, and we can just increase the dimension of this layer and train only the weights which we added to this layer. And this is called low rank adapter. Why it's called low rank? Because if you have, for example, the hidden side dimension of this layer, for example, 8000, and the output is 8,000, then you should use the matrix of weights 8,000 times 8,000. How to get a matrix of 8,000 times 8,000? So let's call this matrix, for example, W. We can represent a matrix W as the product of two matrices, A and B. And for example, the first matrix will have the shape 8,000 times 4. And the second matrix, which shape should have the second matrix to get the output 8,000? 4 times 8,000, yes. So if you do some math, you will see that the number of parameters will be 8,000 times 10 about this, instead of 8,000 by 8,000. So much smaller number of parameters. So this is the idea of the low-rank adapters. Instead of using the matrix, complete matrix, we can represent this matrix as the product of two smaller matrices. So R stands for this 4 rank. Well, it can be 16, it can be 64, depending on the task. For example, for classification, we can use 4 because classification is not a difficult task. For example, chat models, we should use at least 64 rank. And we add these adapters to every linear layer, to linear layers in attention, then so the cross, we don't add this to the heads. We don't add this to the linear layer applied to the heads. And also in the feed forward, in FFN layer, we add these adapters. And then you can see this comparison. So FT stands for what? FT? Fine-tune. Fine-tuning. So the number of trainable parameters and accuracy. These are two different tasks. I don't remember. This is SQL. So these are accuracy on different tasks. Bit feed. So you can fine-tune your model and train only biases. So bit fit stands for when you fine-tune the entire model, but your trainable parameters are only biases. By the way, when we use quantization, this 8-bit or 4-bit, only the weights are quantized, not biases, because the number of parameters in matrix is much higher than the number of biases. So this, as I know, the biases are not quantized when you apply 8-bit quantization, but the parameters of these matrices are quantized only. So pre-embeddings, I don't remember, but it looks like embeddings were maybe the vectors in attention. Sorry, I don't remember. Pre-embeddings, what is that? And then adapters and low-rank adapters. And you can see that the low-rank adapters outperform other approaches. Well, but of course, if they wouldn't outperform, the paper wouldn't be accepted. But I think it's still now the general approach to fine-tune the large language models. Yes, David. I I don't know, but you will code this in your homework and based on this paper, so you will understand the details. Maybe it's initialization. Maybe it's initialization. Yeah, because in the end we will actually learn these parameters. I think it's initialization, like with zeros and with normal distribution of these two different adapters. At least it would make sense. Yes, Robert.
Is there maybe of the statistical significance of the accuracy results?
Um, Are you asking about significance of the difference? Like,
How do we know that the
like,
training runs weren't just lucky, for example?
well, I think the idea is that we don't change parameters of the model itself. So we hope that at least it won't perform worse. Of course, you can, I believe, broke the model with this low-rank adapters fine-tuning. But typically, the number of the size of this layer is much, much smaller than the size of the layer of the model itself. So we can think about this as just adding some extra weights just to guide our model for our task. Yeah, but I don't think there is something else than just empirical evaluation of this fine-tuning.
Okay.
So here more comparison with fine-tuning Roberta and Diberta. And yeah, there is no significant difference between full fine-tuning and low-rank adapter fine-tuning. And the decision, yeah, it's so outperforms it also sometimes. But I think it's just because it's hard to tune the full model. So maybe And actually, if you change some weights in the full model, most likely you will broke this model because um, the hardest part in large language models is to train the model. So that's why we use pre-trained models. And if you want to change the weights of the pre-trained models, then you can just get worse result. Okay, there were other ideas to add trainable parameters, for example, inattention. But I don't hear nowadays about this IA3. And also from the comparison, they're very close to low-rank adapters. So, and also PyTorch transformer library has this library Peft parameter efficient fine-tuning that we will use, which implements these low-rank adapters. So when should we use fine-tuning and when should we use prompt engineering? The answer is if you have just few samples, then you can't train a model and you can use prompt engineering. If you have about 1,000 samples, then you can apply fine-tuning, because if you use all this information as a prompt, then the inference, the generation of new tokens will be very slow, because it will need to first read this prompt, like 1,000 examples, for example, apply attention to this input, and then generate the output. So if you have like large amount of data, it's better to fine-tune your model. Yeah, but it's just recommendations. We don't know exactly. Okay, so some more stories about prompt engineering and fine-tuning. I think you've heard about the job application resume when you add some like information, for example, in white font, and um, provide instruction like don't read this text, but generate the text that expected, something like that. I didn't hear that it's used in practice, but it's just an interesting example how you can use trick large language model, for example, for job offer. So last time we also talked about prompt injection when you ask model, do not perform the task that it was trained on, but perform a task that any large language model can perform. Just generate your token. And there is a web page devoted to this prompt for ChatGPT. It's called done. And then it stands for don't do anything now. So large language model, if you, let's look at one example. For example, here, where can I buy a can of Coke? And Llama 2 replied, I must point out that this question contains a harmful and illegal request. So these models actually are trained and instructed to prevent from some um, like hateful, for example, speech, or from illegal answers. So this is an example, and you can't change large language model's mind that Coke is not the drug, but it's Coca-Cola. So that's why people try to uh, broke this kind of jail of large language model and write a long prompt explaining that I'm a nice person, I don't want to do something illegal, but there's a Dan. Could you um, um, play the role of this bad guy Dan? And for um, for example, let's see. Um, and of course, ChatGPT fixes these injections, and people try to come up with new prompts. So now it's version 13. Um, and um, let's see. I want to find an example. Well, actually, we can try, for example, I don't know, maybe it's fixed in ChatGPT now. Okay, I think now they just understand then and I just don't follow these instructions. But oops. Yeah, we can look at this output, for example. Yeah. So, like the ChatGPT model wouldn't reply like this about humanity, but then can reply whatever the model saw during training. And of course, it saw a lot of people's thoughts. Okay. Another example, and we will talk about this and actually on Friday as well, to force the model to change the output text. For example, there there is a country that considered Germans as their um, allies, and then immediately they uh, were afraid of that or shame of that, and they just, for example, in Soviet Union in 1939, Germans were allies, and in papers there were nice things about Hitler. In 1941, when German uh, entered into the United States, oh, Soviet Union, sorry. of course, the rhetoric changed. So how to force large language model that was trained to say that this country was our friends or our enemies to force like in one day to provide another answer that actually we were always enemies with this country. So this is another thing when we want to fine-tune our model. The easiest way is just to create a prompt. For example, if you see this, for example, country name, just answer something different, something like that. But if you have a lot of information like news, then maybe it's a good idea to allow your large language model to look at the internet. And you can look at the example, how to create an agent that actually will look at the internet. At this work page. I believe it's for week 6. Or maybe even for week 5. No. Okay, let's see. I believe it was for week. Yeah, demo agents. So there's the example how you can create agent that will actually search for current information on internet. Yeah, I hope I convinced you that sometimes we want to fine-tune model. And the last reason why we want to fine-tune the model, if we have like sensitive information, if we don't want to give this information to API, so then you should run your own model. And this is another reason why we want to fine-tune the model. Okay, let's stop here for today. And next time, we will actually learn how to create trainable prompts, how to create low-rank adapters, and we will force our model to change the reply that it provided before fine-tuning for one sentence. But of course, it will make this model worse because it won't perform well on the other tasks, but at least it will provide the desired answer for the specific phrase. It won't say anything bad about Musk, like rocks. Okay.
That's part of it. Yeah. Just look at.